Welcome! In this video, we introduce the theory, common applications, an example of the machine operations, and a result analysis of X-ray diffraction. XRD is a non-destructive experimental technique allowing characterizations to be done without distorting or destroying the sample. This is useful as it allows the same sample to be able to be reused for other characterizations. It works to characterize materials that are crystalline in nature. It can be used in both surface and bulk analysis. XRD can be used to determine phase composition, crystal structure orientation and size, lattice strain, preferred orientation, layer thickness, and more. XRD works through the X-ray scattering of atoms. Electrons in the atomic shell interact with X-rays, causing deflections. X-rays are electromagnetic waves with high energy and short wavelengths, comparable to the atomic distances. When X-rays hit an atom, they interact primarily with the electron cloud, causing electrons to oscillate. These oscillating electrons then re-emit X-rays in different directions. In XRD, this process is known as elastic scattering, as no energy is lost. The scattered waves maintain their phase relationship and can interfere constructively or destructively, forming diffraction patterns. This is the basis of X-ray diffraction, used to determine crystal structures. As mentioned, when an X-ray beam hits the electrons in an atom, the electrons re-emit or scatter the X-rays in different directions. We can describe the change in the X-ray's direction using a scattering vector, which connects the original wave, K0, to the scattered wave, K. This scattering vector carries information about how the atoms are arranged inside the material. Diffraction is a phenomenon that occurs when light waves bend around an obstacle or spread out after passing through a narrow space. The result is an interference pattern seen on the right. Additionally, it is detrimental to the success of this technique that the material under analysis is crystalline in nature. This is significant as crystalline materials have an ordered atomic arrangement, resulting in uniform interference patterns upon diffraction. X-ray diffraction is made up of three main components: the X-ray source, the sample and sample holder, and the X-ray detector. The X-ray beam is created, which is then diffracted by the sample and collected by the X-ray detector. The detector moves in sync with the X-ray source. At certain angles, the X-rays overlap in phase, producing constructive interference. One constructive interference to another occurs in increments of a whole number wavelengths n. By measuring the angle of the scattered rays and knowing how many extra wavelengths are traveled, we can calculate the space between atomic planes. This relationship is given by Bragg's law. It is mentioned that XRD works for materials that are crystalline in nature. This is so that uniform interference patterns can be detected to allow for usable data to be extracted for analyzation, as seen on the top. In contrast, amorphous materials have an irregular arrangement of atoms and do not lead to material-specific interference patterns. Powder XRD is what will be demonstrated for this video. Powder XRD are used when large enough crystals are not available and thus analyzes the many smaller crystals. It provides information about the crystal phases present in the sample, phase composition, particle size, its strain, and orientation. XRD is used in many applications in the department, including the single crystal XRD analysis of inorganic materials and macromolecules, as well as powder XRD of inorganic compounds such as catalysts. Single crystal XRD analysis allows the determination of the complete structure of the material at hand. An example sample measurement can be seen here. First, the sample needs to be prepared. Many different sample holders exist. For this example, this holder will be used. First, take the sample. With a mortar and pestle, crush the solid sample into a uniform homogeneous powder. Set this aside. Have ready your sample, sample holder, spatula, and glass plate. Using a spatula, place some of your sample into the sample holder. Flatten this out using a glass plate and remove excess powder that is outside of the indicated circle. Inside the machine, you can see on the right the X-ray tube, in the middle the sample holders, and on the left the X-ray detectors. Turn on the thermostat for X-ray tube cooling using this switch. Press the green button to turn on the machine. This will prompt this noise to be made. Press the blinking white button to lock the machine, deactivating the noise. Open the MiniFlex program on the computer. Under Control and XG Control, set the voltage and current. Once set, you should see the XRD X-ray light turn on. Select the measurement package, in this case, General Measurement. If you cannot see this tab, go to View, Flow Bar, and Package/Macro Measurement. Select a save location for the data. If you have more than one sample, check the boxes on the left to save the data, and check the boxes on the right to make sure that the samples rotate. Select the sample speed on the fourth column. The slower the degrees per minute, the more accurate the data, but will require more time. Set the speed according to the sample. If you are unsure about your sample, start with a faster speed and adjust accordingly. Place your prepared sample into the machine. Click OK on the top left corner of the computer. A new pop-up should show that general measurement is being executed. The resulting plot depicts the intensity of the signal for various angles of diffraction at their respective 2 theta positions. These peak corresponds to very specific values of spacing between the crystals or atoms in the sample that can be calculated via Bragg's law. These values were calculated and shown in the table here. The intensity of the peaks via constructive interference is related to the amount of phase, or with that specific spacing. The greater the intensity of the peak, the greater the number of atoms arranged with that particular spacing. In other words, the intensity of a specific peak correlates to the amount of one particular chemical species within the sample. After analyzing all the different peaks together, we can determine the composition of our sample material. The width of the peak should be measured by the width at 1/2 of the maximum intensity height. This is inversely proportional to the crystal size, which can be calculated by Schirer's equation. Here, d is the crystal size, k is the Schirer's constant, and beta is the width at 1/2 maximum peak height. Therefore, a thinner peak equates to a larger crystal, while a broader peak can suggest smaller crystal size, amorphous character, or lattice imperfections. In this specific plot, several sharp, intense peaks are observed at characteristic 2 theta values. The sharpness of the peaks indicate a high degree of crystallinity. The presence of only well-defined peaks without significant broad humps also suggests that the sample lacks amorphous impurities. Thus, the XRD analysis confirms that the sample is highly crystalline cubic silicon carbide.
This concludes the video on XRD. Thank you for watching.